Hello, so this is section 3.4. Today's topic is equations and graphs of polynomial functions. So this is the last section of chapter 3, and today we're going to really bring in things from section 3.1 and 3.2 and 3.3 and bring it all together. So first, we're going to be looking at these three functions here, and we're going to be graphing it and making some observations. So before we start, I'm just going to point out some of the things that we should already observe or can see from here. First is, with the first graph, we're just going to point out the degrees and leading coefficients of each of the graphs. For the first graph, it's a degree 3 and a leading coefficient of 1, okay? For the next graph, the degree, so looking at how many factors there are 4 of them. Keep in mind of this square there, okay? So it's degree 4 and leading coefficient of 1. And for the last one, we do have a cube, so there's actually 4 of these brackets. So we do have a degree 4 and a leading coefficient of 1 as well. So with these graphs, I recommend you to go to Desmos to punch them in to see what they look like. I'm going to be just drawing a sketch with some key points. They're not going to be 100% accurate, but I do expect the x-intercepts to be labeled and in the correct spots, and the y-intercepts. These two I expect to be in the right place. The kind of max and the mins, I'm okay with it being a bit off, okay? So with the first one here, you will notice that there are x-intercepts at -3, -1, and 1. And there is also a y-intercept at -3. Since it's a degree leading coefficient 1, it does make sense that it came from quadrant 3, looped around, passed, and goes up like so. Now keep in mind these graphs do go on forever. So those are some of the key points there. In the second graph, you would notice the x-intercepts are also at the same spot, -3, -1, and 1, but the y-intercept is now at -9. I'm just going to put it down there like that. Since it's a degree 4, it's going to start in quadrant 2, but this time you're going to notice, oops, very shaky line there. You're going to notice that kind of touches, oops, let's try it again. Kind of touches and goes up, and then it goes down through the y-intercept and then back up and crosses through. So it looks something like that, okay? And in our last graph here, we do have just 2 x-intercepts, again at -1 and -3. So it's going to start here, oops. And you're going to notice this time when it goes through -3, it kind of has this like S shape like shape, and then it'll dip down, come up, and then it will eventually pass through the x-intercept. Don't know if you had your graph range that high, but it should be at 27, okay? So those are the 3 graphs. So taking a look at these 3 graphs, let's just look at our x-intercepts. So for the first graph, the x-intercept is at -3, -1, and 1. For the next graph, our x-intercepts is also at -3, -1, and 1. And for the last graph, our x-intercepts are just at -3 and -1. So we're going to skip the multiplicity for now. We're just going to look at some of the points below here. Let's just write this. So the points of any polynomial function corresponds to the x-intercepts of the graph and to the roots of the corresponding equation fx equals to 0. So zeros, x-intercepts, and roots are all identical and mean the same thing. So what I mean by that is when you're looking at x-intercepts, it's when your function basically equals to 0, f of x meaning that y value. Okay, that's how you find your x-intercepts. And the term 0 x-intercepts and roots, they all are identical and mean the same thing. So whenever I use these terms, just know they're all meaning the same thing. Okay, so back to multiplicity. So multiplicity of a zero is the number of times a zero of a polynomial function occurs. So how many times does that zero, or what we call the factor, appear, right? So as you can tell with the zeros, basically it comes from each of these brackets here. So once we set that f of x to 0, we just treat it kind of like how we would with a quadratic equation. You'll just set each bracket to 0. So looking at each of our x-intercepts, I'm just going to write these out. Let's look at our multiplicity. So each of these in the first function, there's only one of them. So therefore, they each have a multiplicity of 1. I'm just going to use m to represent multiplicity. Looking at our second one, well, x equals to -1. Keep in mind you have to switch out the sign when you're finding the root. So x equals to -1 and 1 both just have 1 factor, so we call multiplicity of 1. But this one actually is squared, so there's 2 brackets that are x plus 3. So the root of it being x equals to -3 is actually 2 of them. Now looking at the third example, we have -3 and -1. The -3, since there's a cube, we have actually multiplicity of 3 and multiplicity of 1. So now I just want you to quickly just to take a look at, well, when it's multiplicity of 1, what does the graph look like around those roots or x-intercepts? If you have a multiplicity of 2, what does that look like? And multiplicity of 3, what does that look like? And as you can see, I'm just going to use different colors. Multiplicity of 1, they kind of have this look where they kind of just go through the line. You're just going to highlight those here. Multiplicity of 2, well, it's a little different, right? It kind of just dips and just touches the line and then it kind of bounces off again. And then multiplicity of 3, well, we have this kind of S-shaped thing. It still cuts through, but it's not a straight cut through like how multiplicity of 1 does. So let's just make a note on some of our observations here. So what do we notice about odd multiplicities? So odd, remember, as 1, 3, 5, la la la. So from what we saw, it seems like with odd multiplicities, that line just always cuts through the x-intercept from one side to the other. So I'm just going to write a note that line from function will cut through, oops, can't spell, will cut through the x-intercept, cut through the x-intercept, yeah. From positive to negative, or negative to positive. So it goes right through, okay? Now, the even multiplicities, the only example that we're seeing here is just 2. The line will touch the x-intercept, but will stay on the same side. So what I mean by that is kind of like when we have, like with our example up here, it comes in from the positive side here, but it won't go through. It'll just kind of touch and then it'll bounce back up. Okay, that's what I mean by stay on the same side. If it's on the positive y, it'll stay in the positive y. If it was in the negative y, it'll stay in the negative y. Okay, so now that we know kind of some more terms, let's just look at some more graphs. So we have these two particular graphs here. We're just going to start with the one on the left, this red one. So looking at this, what is the degree? So to determine the degree, we should look at the number of bumps. So here we have one bump. Actually, probably we should start from the left side since we're used to that. So looking at this S shape here, this is actually, it's actually equivalent to 2 bumps, okay? So here's bump 1 and here's bump 2, 3, 4, 5 bumps. Remember, degree is bump plus 1, so it's a degree 6. Okay, since it's degree 6, leading coefficient, this one is an even degree, and when you think about it, it's basically opening downwards. So if it starts in 3, ends in 4, this is a negative. We'll just know that it's negative. It's a negative leading coefficient. That's kind of all we know. Zeros. How many zeros do we have? Well, and where are the zeros? So there is a 0 at... where is that there? So that's, it's at x equals to -4, right here. And we have at 1 and at 3. Okay, those are our zeros. And the y-intercept, it's actually this point right here, which is at y equals to 8. Now, regions that are negative. So where is this graph negative? So it's basically just down here and on this side. So when I'm talking about negative, okay? Just those two parts right there. So it's negative when it's smaller. When x is smaller than, what is that, -5? Nope, -4. And it's also negative when x is greater than 3. Put a comma there. Now, regions where it is positive. Well, that is basically the rest of the graph. However, you do have to be very careful, okay? Just because the graph is it looks like the rest of the graph is above y, but there are these x-intercept points. These x-intercept points. And these x-intercept points, since it's at 0, it's neither positive nor negative. So they don't really count. So the regions that are positive is basically when x is between -4, and 3, but x cannot be at 2. Okay, so, or sorry, not 2, that's 1. Not at 1. This point here is at 0. Okay, looking at our other example here, graph on the right, we do have 1, 2, 3, 4 bumps this time. So we have a degree 5 leading coefficient. With that particular shape, you should recognize this is a positive leading coefficient. Zeros are at -3 and at -2 and at 1. Y-intercept is actually over here, which is y equals to -9. And the regions negative is anything that is below the x-axis, which is going to be when x is smaller than -3, when x is, when x is between -3 and -2, and when x is between -1 and 1. Regions where it is positive is when x is between -2 and 1, and also when x is greater than 1. Okay, so that's just some information we know about these graphs. All right, moving on to our next example. So now we're not looking at a graph, we're looking at a function, and we need to figure out some of these, some of this information. So first off, let's look at our degree. Since we have three kind of factors here, x times x times x, we know at most it could be x cubed. So we are looking at degree 3. Now, the lead coefficient. So when you think about it, if you multiply out these x's, we have x to the 3, and then this -2 basically will just multiply in. So our lead coefficient must be -2. I'm going to erase that. Now, since we're doing degree 3 with a negative leading coefficient, we already know the shape must look something like that, right? 2 bumps starting from 2 and ends in 4. So it's going to start in 2, ends in 4. We already know the shape will be something like that. Now, what are the x-intercepts with multiplicity? So remember, x-intercepts, we're just going to set y equals to 0. So in that particular case, our x-intercepts include, if y was equal to 0, then this is going to be x equals to -1. Here is x equals to -1, and x equals to 4. So the x-intercepts include x equals to -1, but what's my multiplicity? I have 2 of them, so it's going to be to the 2. And we also have x equals to 4, and here we only have 1, so multiplicity of 1. Actually going to make this a little bigger. All right, and now the y-intercepts. So when you think about with y-intercepts, you're going to be just multiplying out this last number. So in this particular case, okay, and why we're multiplying just those last numbers, oh, and this number here, is because y-intercepts is when x equals to 0. And when we put 0 there, all we're left with is y must equal to -2 times 1 times 1 times, oh, let's erase this. Can't see them. If it's plus or minus. 1, 1, and -4. So that leaves us with 8. So now with this information, let's do a quick sketch in order to figure out our regions, positive or negative. So here's our graph. Our x-intercepts, we know we're at -1, and 1, 2, 3, 4. We know it's at 4. This is a degree 3. Again, we already mentioned that the shape's going to look something like that. Multiplicity of 2. So at -1, we know it's going to touch and then bounce back up. Oh, and then we have a y-intercept at 8. Let's say that's 8. It's going to cross the y-intercept, and then it's going to go through our other point here. Da-da-da-da. It's going to look something like that. So where are the regions that are negative? Well, it's really just this part down here. So therefore, that's when x is greater than 4. Remember, it's not equal to 4 because exactly at 4, the number is 0. So it's neither positive or negative. Now, where are the parts that are positive? Well, positive parts are here. So that basically, there's a couple ways of writing it. I'm just going to write it this way. It's going to be anything that when x is less than 4, but x cannot be -1. Okay? Anything but that, then we're looking at regions that are positive. Put a comma there. Okay? All right. Last example. So far today, we've always looked at things that were already factored, which is nice, but it's not always going to be the case. So here we go. Here is back to 3.3. So with our, the first thing we can do here is we can actually factor it out to make our polynomial a little easier to deal with. So let's just first take out that 2. So we have x to the 3 minus 4x2 plus 5x minus 2. So now that we're working with a polynomial where our leading coefficient is just 1, then our life is a lot easier. So first off, we need to look at our constant term. What are the factors? So we can work with either plus minus 1, plus minus 2. So from here, we're just going to test one out. So let's just say, use our remainder theorem. So let's just say k equals to 1. So let's put in 1. So 1 to the 3 minus 4, 1 to the 2 plus 5, 1 minus 2. So that gives us 1 minus 4 plus 5 minus 2. So in this particular case, we have -6, and this gives us 0. Yay! So what does that tell us? That tells us that x minus 1 is a factor. So now it's just a matter of finding out what are the other factors. So again, I'm going to use synthetic division. You can choose whatever you choose. So I'm going to have this, this polynomial here divided by x minus 1. So I have 1, -4, 5, -2. Bring this down, so I have 1, -1 times 1 is -1, -4 minus -1, so that is -3. So multiply, it will be 3 minus 2, multiply, and that's -2 minus 0. Again, since you know it's a factor, if this part remainder is not a 0, you have done a mistake somewhere. All right, so that means we know that we're dealing with x squared minus 3x plus 2 times our x plus 1 is our function here. Now, can we factor this more? I think we can. So it'll be x minus 2, x minus 1 times x plus 1. And this, or I guess, and we have our 2 out front. This is equal to our y. Yay, oops, yay. So with this, let's figure out some information we have below. So our degree is 3. Our lead coefficient is 2. The end behavior starts, well, since it's a degree 3 and it's positive, should look something like that, right? It'll start in 3 and in 1. X-intercept, So looking at those zeros from here, we do know that we have x equals to 2, which has a multiplicity of 1. We also have x equals to 1, which is also a multiplicity of 1. And we finally have x equals to -1, which is also a multiplicity of 1. Y-intercepts. So again, we're just going to set x to equal to 0. I'm just going to write that down as a note. So that means we're left with y equals to 2 times -2, -1, and 1. And that is 4. Okay, regions negative and positive might help with a sketch of a graph. Boom, boom. So our x-intercepts are at -1 and at 1, 2. Ooh. Okay, and our y-intercept is at 4. Let's just say 4 is up there. So it's going to start down here. Gonna cross, come down, and then go back up. So it's gonna look something like that. So regions that are negative are gonna be anywhere down here, which includes when x is smaller than -1 and when x is between 1 and 2. Regions that are positive will be here and here, which means that is when x is between -1 and 1, and when x is greater than 2. Okay? So that is a wrap for chapter 3.